Okay, when we did our last lecture, one of the things that is new now is this term right here that you have in your lecture notes, but I did not have in mine. This is the center-seeking acceleration magnitude. So notice that the only difference is that this does not have the negative r hat, which is your direction. Okay, and again, just a reminder that the velocity is going to be speed is going to be 2 pi r over t, and that the time period is 1 over f, which is the frequency. Okay, so let's go ahead and do the first example. We have a carnival clown, like Krusty, who's riding a motorcycle down a ramp and around a loop-the-loop. If the loop has a radius of 18.0 meters, what is the slowest speed the rider can have at the top of the loop to avoid falling? Now they give you a hint for this problem. Notice the hint. It says the normal force will go to 0 once the motorcycle just leaves the surface. So as soon as that motorcycle just leaves the surface of the ramp, the normal force disappears because there's no longer a contact. So let's go ahead and write down our given information. We know that the radius is given. It is equal to 18.0 meters. Okay. We also know that the acceleration due to gravity is a constant. So I'm going to put g is equal to 9.8 meters per second squared. Some of you may be saying, wait a minute, Dr. H, isn't that negative? Notice that I didn't put a vector sign on the g here, so I only want the magnitude of g. Okay. Let's see. Unknown. We want the speed, the slowest speed. So v minimum. Basic equations. Let's see. I am given the sum of the forces equals ma. And because this is traveling a loop-the-loop, I know that a sub c with a vector sign is equal to negative v squared over r hat. Okay. So let's go ahead and, I'll probably need the weight. So force on cycle by Earth, let's put a vector sign, is equal to mg. Okay, so the first thing I'm going to do is I'm going to draw my free body diagram. Notice that I've already indicated here where the center is. So this is the center of the loop. I'm drawing a free body diagram at the top. So if this is my loop, I'm drawing my free body diagram at this point, and this is the center of the loop. Okay, so what's physically touching the motorcycle? Now that's a trick. You may be saying, well, it's the ramp, of course, or the loop-the-loop. And that would be true, except we want to have the slowest speed possible. That's going to occur when that normal force just goes to 0. So the ramp is no longer touching at the very top. That's going to be the minimum. What's acting at a distance? The Earth. So I'm going to go ahead and draw my free body diagram. And I have force on cycle by Earth. And if you want, you can make that blue. I can't make it blue. My blue isn't working right now. Okay, you should make that blue just to help you out. Okay, again, normal force is 0 because we want the minimum speed. That's your hint. Okay, so now that we've drawn our free body diagram, what we're going to do is we're going to go ahead and solve Newton's second law. We know that the sum of the forces are equal to ma. Okay, looking at my diagram, am I accelerating? Yes, I am. How do I know? I only have one force acting on it. If I had two forces and one was acting up and one was acting down and they were the same length, I could say, yeah, fine, I'm in equilibrium. But I only have one force, and that means that I'm not in equilibrium. Okay, so I'm going to keep the A, Newton's first law. Okay, next step, substitute in from the free body diagram. I have force on cycle by Earth, vector sign, is equal to m. Now what I'm going to do is I'm going to replace this with an ma sub c, where the subscript c means centripetal, but remember, centripetal means center seeking. Okay. What I have done is I have gotten into the habit of just using the word center seeking so that I do not get thrown into this idea that centripetal forces mean extra forces. And unfortunately, that's what ends up happening in our everyday life. When we think of centripetal, we immediately think that it's that force that throws us outward, right? Because that's the way we want to go. But remember, that's your inertia. That has nothing to do with the forces that are actually acting on the object. Okay, in this case, I'm not going to use my r hat when I substitute in because I already have a direction for this. Okay, my direction from my free body diagram is down. It's going to be in the negative j hat direction. So even though on this sheet we have a direction of r hat, that's because r hat would be here, or here, or here, or here, or here, or here, or here. Okay? R hat gives you the ability to say it always points to the center of the circle. Okay? So that's why I like using negative r hat when it comes to the formula right here, negative r hat. But when we're solving this problem, it's not realistic for us to use negative r hat because we already know the direction of this force. So what I'm going to do now is I'm going to substitute in magnitude and direction. I end up with negative mg j hat is equal to, now what is the direction of our center seeking force? It's to the center. Where's our center? In the negative j hat direction from the point of where the cycle is. So now I'm going to substitute in negative mv squared over r j hat. Okay, now I'm going to substitute, or I'm sorry, I'm going to solve for v. I'm going to cross out the j hats from both sides. I'm going to cross out the negatives. I'm going to cross out the m's. The m's cancel out because I have m on both sides. I end up with v squared over r equals g. If I multiply both sides by r, I end up with v squared equals rg. If I take the square root of both sides, I end up with v equals the square root of rg. Now all I have to do is substitute in the numbers. Okay, so r is equal to 18 meters. So we end up with 18 meters times 9.8 meters per second squared. Okay, why did I not include the negative in that? That's right. The negative doesn't get included because I want the magnitude only, not the magnitude and the direction. Okay, so I'm going to substitute this into my calculator. Let's see what we get. I end up with 18 times 9.8, and then I take the square root of that, and I end up with, I need how many sig figs? I have 3 here, but this is a constant, so it doesn't count. So I have to have 3 sig figs, and my answer is going to be 13.3 meters per second. Am I sure it's meters per second? Well, here I have a meter times a meter, which gives me meters squared. If I take the square root of that, that gives me a meter. Here I have seconds squared in the denominator. If I take the square root of seconds squared, I end up with 1 over seconds, which I have here. So the units check. So my answer is 13.3 meters per second. That's how fast the motorcycle has to go in order to make it around the loop. Okay, in the next video, we'll cover the next problem.